When you picture getting stranded in space, you probably imagine freezing in the dark. But for a modern spacecraft, the real threat is exactly the opposite. Out in the vacuum, there's no air to whisk away heat. That turns a highly insulated capsule into the ultimate thermos. It traps over 100 watts of body heat from every astronaut inside, and that's before you even factor in the avionics. Those flight computers and life support systems generate a massive compounding thermal load. So, to keep the crew from essentially roasting alive, aerospace engineers had to build a circulatory system for the ship. It's a multi-stage thermal architecture designed to hunt down every stray joule of heat in the cabin and pump it outside. This whole heat rejection process comes down to moving fluid. It absorbs the heat from the delicate electronics in the crew, pulling it away from the pressure vessel. Eventually, all that heat makes its way down into the massive curved radiators built right into the unpressurized trunk. The survival sequence starts inside the cabin with the heat acquisition loop. It pulls heat from the cabin air and the flight computers. Because it runs right next to the crew, this internal loop uses a strictly water-based fluid. Toxic refrigerants inside a sealed pressure vessel are an absolute non-starter, so engineers just pump plain water through cold plates beneath the electronics. The water silently soaks up the mounting heat from the hardware. If it didn't, you'd get a runaway thermal cascade that could fry the navigation computers, leaving the capsule completely stranded in orbit. But you can't just vent that boiling water out into the vacuum. Instead, it's routed to a critical thermal bridge, known as the internal heat exchanger. Here, that safe water loop runs right alongside an external cooling circuit, which is filled with a much more aggressive fluid, something space-rated, like ammonia or a synthetic coolant, designed to survive the freezing shadows of orbit. Without the fluids ever touching, heat passes right through the thin metal walls of the exchanger. It's a clean handoff, taking that dangerous thermal load from the crew compartment and dumping it into the exterior plumbing, where the fluid is forced down, into the massive, unpressurized trunk at the base of the vehicle. Once that superheated coolant reaches the trunk, it gets pumped through a vast network of radiator panels wrapped completely around the lower cylinder. Now, because space is a vacuum, you can't just rely on air blowing over the fins to whisk that heat away like you would with a car radiator. Instead, these panels have to rely purely on thermal radiation. They bleed all that collected energy out into the void as invisible infrared light. But doing that effectively in the vacuum of space takes a massive amount of surface area. So the fluid snakes through hundreds of microscopic channels beneath the hull, gradually cooling down as it completes its long loop around the trunk. Once chilled, it's pumped all the way back up into the capsule, ready to soak up another round of heat from the crew and those hard-working flight computers. It's a continuous, delicate dance that keeps the internal climate perfectly balanced for months on end. But there's a catch. This elegant thermal system hides a terrifying vulnerability right when the crew enters the most dangerous phase of the mission, the return to Earth. Because the trunk is completely unpressurized and lacks a heavy heat shield, it has absolutely no chance of surviving the brutal friction of atmospheric re-entry. So, it has to be intentionally jettisoned shortly before the capsule slams into the upper atmosphere. The moment separation happens, the fluid umbilical lines are severed, leaving the entire primary radiator system behind to burn up. Suddenly, the astronauts are trapped inside a perfectly sealed, heavily insulated thermos. The flight computers and life support systems are still generating massive amounts of heat, but now there's absolutely nowhere for that compounding thermal energy to go. It instantly becomes a race against time before the cabin cooks itself from the inside out. Ultimately, survival in orbit boils down to these strict laws of thermodynamics, rules that completely shatter our intuitive, earthbound understanding of temperature. Because the freezing cold of the void? It's kind of an engineering illusion. A perfect vacuum actually acts as the most effective insulator ever conceived. Your primary enemy isn't the freezing environment trying to get in, it's your own internal energy desperately fighting for a way out. The lack of a medium to carry away that waste heat is far more lethal than the freezing dark itself. So, how would you engineer a fail-safe, passive cooling system for a long-duration trip to Mars? Drop your theories in the comments and make sure to subscribe to join the conversation. Stay curious, and we'll see you out there next time.